Is my background sound is it too loud or no? No, right? Okay. Okay, so let's just take a look what we have in the morning session. So in the morning sessions, we develop a new sections on the matrix that we call it an eigenvalue and eigenvectors. Okay? And then we have performing diagonalization to find the diagonal matrix, okay, which has this property, okay, which has the property. So basically, the question is, okay, if it's asking about eigenvalue, usually the typical question that it has, it will asking the eigenvalues, it will asking the eigenvectors, and of course, if you find eigenvalues and eigenvectors, you can find the diagonalization. So you can diagonalize the matrix and find the matrix D, or the diagonal matrix. Okay. So uh, if you look here, maybe before we go into more detail, maybe let me just go to look at the there is another note that I forgot to mention about these diagonalizations. So there is some statement that uh, that is important to you. Let me go. Okay, here. Okay, so to diagonalize the matrix A, first the conditions that need to be prepared is the matrix A, it need to have unique eigenvalues. Okay, and then the second, the matrix A need to have they may have multiple eigenvalues if they are linearly independent. So this is becomes important, okay? Linearly independent. So one thing that I may write here is, maybe let me write here. Okay. Let me make this smaller. Let me make all this smaller. Okay. Let me write notes. So matrix that is not diagonalizable. Okay, consider matrix. Let me just give you a brief example. Okay. 3, -1, 4, 7. Now, if we check the eigenvalues, if you want to check the eigenvalues, it will have the repeated eigenvalues. 5. Okay. So it has, let me just write, it has repeated eigenvalues. And then as in implications, because of repetitions, the matrix A is not diagonalizable. Okay, because it has repeated eigenvalues, which means why it's not diagonalizable? Because the repeated eigenvalues means that it is not linearly independent. Okay, so let me also write eigenvalues not linearly independent. Okay, or you can just, when you calculate, you see the repeated eigenvalues, then it's not diagonalizable. Okay. And then the rest, I think we'll skip for the matrix. Okay, just until here. Okay, so eigenvalues, eigenvectors, diagonalization. Okay, now we move on to now vector calculus. Okay, so vector calculus, what I want to start with is in calculus 2, we may have learned that you have learned about the first the vector functions. Okay, so let me just give you some quick review and maybe just as an introductions that consider these two conditions. Okay, first is we have two dimensions, and we can set some curve C, and we can set a parametric curve. Okay, we can set a parametric curve. This parametric curve with variables t, and we can set the vectors or vector positions. So this is a vector positions according to this R. Okay, according to this R. So R at t0 it depends on the parametric x and y, and with variables t. Okay, so we can have maybe it's same. Okay, this one. Okay, and then if we draw in 3 dimensions, we can also set up our curve, and we can define the positions of the vector as the R. Okay, so we can have a parametric with variables t also. Okay, and then we also have learned about the motion on the curve, the curvature, right? So let me just list some idea that you need to review by yourself. Okay. So first is idea on, of course, the vector functions, and then idea on a partial derivatives, directional derivatives. At least try to look at the basic definitions of it. And then the tangent plane. Okay, and I think this is for the first part. The second part is the double integrals, right? We have learned this before. The double integrals, the Jacobians, the change of variable. Okay, at least this is some of ideas in the vector calculus that you need to look at from calculus 2. Okay, so I will start with our vector calculus in our course. We will start with the curl and divergence. The curl and divergence. So what is curl and divergence? Okay, recall from here, we may write a vector function through our parametric, or let me just write a vector functions. Let me write vector functions. And define this vector function as the vector fields. So vector functions, maybe this is not need to write here. Vector functions of 2 or 3 or more, or maybe 2 or 3 variables. Which means that we can define this, let's say with capital F, x, y. We can define with a vector. Let's say we have a p, function p, with the standard base vectors, and plus Q J. This is for 2 dimensions. And if we have 3 variables, we might add another functions. So P Q, oh, should be Z, sorry. And R. Okay. So to represent these fields in probably in physics, we can have like airflows, the the positive and negative charge, how the force is represented. Okay, let me check with whether I have the picture. Oh, I have here. Okay, so probably here is some of the examples on how we can represent what the vector fields. Okay, so I think it's easy to see that we may have uh, like arrow like that. It has direction, it has some value, and we can define it as a vector, right? And we have like in the field we have like so many vectors that has their own direction. Okay, if you have the in the artery here, the like flow of blood flow, and we have the force field here. It's going to be into one point here, okay, and we have the positive charge. Okay, we have 2 positive charge. The vector field is the force is going out. Okay, okay. This is just an examples on how we can represent the vector fields in physics. Okay. Okay. Now, if we want to represent, for example, if we have vector fields, okay, we have vector fields, negative y I, okay, plus x j. So if you would like to take this into graph, so let's say we start from x equal 1. If we take this 1, let me take this negative 1, negative 1, 1. Okay. Now at this 1, 0, so at 1, 0, what will happen? At 1, 0, this going up. Let me just give you some examples. So at 1, at 1, 0, what happened is 0i, right? Or just 0, and then we have plus j. So it goes up 1 unit, okay, of j. Let's say we have this until here. Or maybe using the red color. I think it's going to be more distinct. Okay. And then let's say we have f at 0, 1. So we will have negative I, right? Negative 1, and then plus 0. So we will go negative to the left, right? Yeah, we are going to have a negative I. Negative I is here. Okay. So let's just take this 1, negative 1, negative 1. So let's take negative 1. So this will be 0, and then minus minus j, minus j, minus j, so it's going to be going down 1 unit. Okay, and then going one more here, we get this is going to be -1, so it's going to be positive I, and then 0, and then 0. Okay, positive I is x-axis, so it's going to be going to the right 1 unit, or maybe going to be a little bit down here, so I can draw a little bit down. Okay, so that's some of the points, and maybe increase a little bit more, maybe start with this point 1 1. So f11 is negative I plus j, so we have negative I and plus j. So what we are going to do, so from this perspective, from this point, let me make, so going to the, this is negative I, this is plus j, so we will have a factor that is going to be like this, right? That is our factor. Now doing the same thing from here, this is negative 1 1. Okay, what we happen, we have that, so we will have negative I and then negative j. So negative I is going to the left, negative j is going to the bottom like that. So we will have like that. And if you try another one, maybe here and here, you will notice that it should be going to here. Okay, and you notice that from what we have, and if you are increasing your points, you will see that the picture is changing or not changing. It has some pattern. So let's say we start from here, going here, right? And then going here and going here. It's like a circle. And if you increase more and more, it's going to be here, going to be here, going to be here, going to be here. Okay, it's another circle. And if you increase more, it's going to be another circle, and another circle. So we can see that we would draw um, the vector fields through some graphs. Okay. Okay, that's just example on how we draw the vector fields. Okay, and then we also recall. So let me write recall. We have the del operator in our partial derivative. Let me just write what is del operator. We usually write the del as this triangle with upside down. Okay, so the del is partial x this is our del operators. So we can write, if we combine this del with some scalar function, let's say we have a scalar function, let's say we have this scalar functions, and if we multiply with, so del with this scalar functions, this is actually what we have as a vector fields. So vector fields is basically the del operator, or the partial of the scalar functions. So we can write down that this becomes the partial x of this function, this scalar function, and then in x-axis, or maybe let me write in more clean. Okay, so that is vector fields. We can write the vector fields as a del operator multiplied with the scalar function. Okay. We call this the gradient. Gradient of these functions, or we can just say it's gradient field. Or maybe we can also say a gradient vector also. Okay. Now from here, from this del, we'll move to definition. Curl of vector field, let's say F, okay, we can write this as curl F equal the partial R partial Y minus partial Q partial Z I and then plus partial P partial Z minus partial R partial X. This is J and then plus partial Q partial X minus partial P partial Y. Okay. Or simply we can say that the curl F is the del cross F. Or maybe let me just write let me just write in the new page, okay, to describe the cross. Okay. If you want to write this first, I will describe in more details. Okay. Let me write here the curl of F is the del cross F. Okay. Let me write a little bit down here. That is, we take I, J, K, and the del is dou X, dou Y, dou Z. This is the function is PQR. Okay. Now we can do the cross as usual. we take the, like we are taking the determinants as we have learned before. So we take the determinant of this part here, multiply with I, and so on and so forth for negative j, for k, okay? And that is why we have this definition here. But I think you can just stick just to this del cross f. Okay? So the curl is del cross f. Or you can use my suggestions, like from previous. We can just add maybe let me write adding I j here. So do x p do y and then q, and then we multiply here and adding all. So do y or do r do y I plus do p do z j, and then plus do key do x k. Okay, the first part, and then minus and then adding all, minus the one that is going to be here, and then we can add do p do y k plus do key do z I plus do r do x j. Just to show you that this also can be worked, and then we can group all I, j, and k. So we will have do r, do y minus do k do z, and then plus minus do r do x, right? And then j, and then plus do k do x minus do p do y. Okay. Okay. Now this is curve, so del cross f. Now notice that the result of the curl is another vector field. Right? This is another vector field, right? Or we say this is a vector, okay, a vector. Okay, I think the curl, I don't need the other explanations. I think in your textbook it has more explanation, but I think just this, I think it's enough. So that's the curl. Now the divergence, it's much more simpler. So the divergence, of vector field f is, we say, div f and we can also write this divergence f is basically the del dot the f. Okay. Okay. Let me write as just a conclusions. Okay. It's a conclusion remarks. So we have okay. So this is, we call the curl of vector field, and this is called the divergence of vector field. Okay. Now this also, because we are having the curl in the cross here, which means that if we are having, of course we have this 3 by 3, right? We can solve this by taking determinants of the matrix, right? But if we have less than 3, then we cannot have any curl. So the curl, we can also say the curl can only be taken in 3 dimensions. Okay. Okay, I think this thing very basic, and I think it's simple enough. Del dot f or del cross f for divergence for curl. Okay, let's say we have some examples, okay, to see what is actually curl and divergence really mean. Okay, and if we can compute that, what does it mean? Okay. Okay, let me check the example. Check first. Okay, I think we can. Okay. Well, let's say let f a vector field has. Let's start with the easy one first, not too difficult, not too complex. Okay. So find divergence f and curl f. I start with the divergence because I think the dot product is practically easier than the cross, right? So let's say the divergence of f is a del dot f. So the partial x squared y plus partial y negative x over y plus partial z x y z. Okay. So directly we can get this will be 2xy. This becomes negative x over y. Differentiate with respect to y becomes multiply with negative and becomes y squared on the bottom. So this will be plus x over y squared and plus differentiate with respect to z just xy. Or we can plus 2 plus 1 3xy plus x over y squared. Now, what this divergence represents, what this representing for? Now, it's becoming a scalar, right? Become a scalar value, which means scalar value means that divergence is basically telling you that how much of vector field is going out of some point. Okay. So the divergence means that it can be going inside like this, or going outside. That's divergence. So this is first part. The second part is finding the curl of F, which means the del cross the vector field. Now we can just write and solve using the product, the cross product. Okay. Now the cross product is I and then minus dou x y z minus dou z x squared y. This will be j. Okay, wait, I will move a little bit left. And then plus dou x of negative x over y and minus dou y x squared y. This is k. Okay, we can solve one by one. This is xz. This has become 0. And then write I standard factor. And then yz, also 0. And then j. And then plus. This will be negative 1 over y. And then minus x squared. And then k. We have the results of the del cross f as xz minus yzj plus, or we can write here, k. Or we can write the curl f okay. Now the curl like we mentioned before, the curl is resulting of vector field. So this is the vector, right? This is a vector. So we can say that the curl resembling or its resulting a vector field and we can also say that it's represent rotation of a vector field. So what this rotations means? Rotations means that we have the direction of curl, which is the axis of rotation, and magnitude of curl is the magnitude of rotation. Okay. Okay. We can discuss more later for what these curl and divergence represent or means. But let me just give you the property of the curl and divergence. Okay. If f has continuous second order partial derivatives, then the del cross the del f, this is zero. Zero vectors or zero matrix. Or we can say this is the curl of the gradient vector of f, so it's zero. Or we can say curl of its gradient is zero vector. And then if now f is a vector field and have continuous second partial derivatives, then the divergence of the curl F, or the del cross F, is 0. So it means that the curl, or let me say this is the curl, like this is the curl. So the curl F, we can say the curl of any conservative vector field is 0. Or maybe let me just write the, oh, it should be here. Sorry, it should be here. The curl of its gradient 0 vector, and we can say that the del cross F is 0. So a gradient, or a conservative vector field. So curl of conservative vector field is 0, and the conservative vector field is basically the gradient of the function. So let me write here. If we have the del F, this practically what we have if we break down. And let's say we are going to prove this this statement. Okay, we are going to prove this statement. Okay. So let's del with this del cross the del F. So we are going to have this is I, J, K, and then the ddx for the del, the dy, and then ddz. So we are going to have this second partials, okay, the second partial. So the del f is the del f del x, del f del y, del f del z. Okay, according to the determinants, we are going to have del y, del f, del z, minus del z, del f, del y. This is I. Okay, we have 3 components. Let me write, sorry. Let me write around here. Make it a little bit smaller. Okay. Okay, and then plus del x, del f, del z, minus del z, del f, del x. So for j, and this should be minus, sorry, it should be minus because the covectors. And then for K is dou y, dou F. Oh, sorry. Should be dou x, dou x, dou F, dou y, and then minus dou y, dou F, dou x. This is for K. Okay. Now let's finish this. This means this is we are going to partial. So first we are going to partial this. Okay. So we can say this is partial f partial z. Okay. So with this the derivatives or the differentiate with respect to z, and then we partial again with respect to y. So we will have, we can write this is as f z y. Okay. And then the second part is fy partial y and partial z. So it means that this is partial yz. This means that we did y first, and then the second one is the z. The differentiation. Okay. And then this is on the x-axis, and then we have this is f zx minus f xz. This is for j. And then for k is f yx and f xy. And remember, from what we have in the calculus 2, the value of f z or zy is equal to f yz, right? So this becomes all 0. So that's why it's becoming 0, 0, 0. So we can say that del cross del f is 0. Okay, this is for the first part. Okay, for the first part, I think to make it easy to understand, let me cut this and make into the other one. Okay, so we can focus on. So let me cut this and put into here first to make it easy to look at. Okay. So first property. So let me go here. Okay, so this is the first property. So let me move a little bit here. So properties of curl and divergence. Okay. So that's the first one. So we prove that the del cross del f is 0. Okay, the second property, so this is the first property. The second property is the one with divergence, the divergence of curl f, which is 0. Okay, so let me just put here, and maybe waiting if you want to take notes first. Okay. right? Okay, the second property. And let's say we are having um, the del is uh, all the partial operators. Okay, let's say we have f is p q z or pqr, and let me write the del cross f. The del cross f. We can write this. Uh, maybe just write with the dou r dou y minus dou q dou z. This is I, and then minus, or maybe writing with the just comma. This comma. I think we can just write this comma. Okay, that's our del cross f as we get the result from the previous pages, right? So we take the del and then dot with the del cross f. So what will happen? So del dot all these terms here. Let me just copy. Wait. Copy. Let's put here. Okay. Now what will happen if we dot these two factors? So we will have a scalar, right? As a scalar. So let me just write dou x, dou y, and dou z, and then we dot with this. So the first part here will be multiplied with dou x. The second part here we will multiply with dou y, and the last part will with the dou z. So dou x we are going to have. We can write like this: dou x dou y minus dou x dou z. Okay, the first part, and then plus, because it's dot product, we plus all the components. Dou squared b dou x dou z. Oh wait. Oh, dou y. Sorry. Okay, and then plus one more. Dou z dou squared q z x, and then minus dou squared b dou z dou y. Okay. Now we can cancel this with this, right? This is q, sorry. And this with this, and this with this, and the result is 0. Okay, the result is 0. So the divergence of a curl, okay, so divergence of a curl is 0. Okay. Or you can also write, because in the previous, the curl one, the first property I'm using with this r, right? R, let's say this is ryx, right? This is qzx, right? And this will be pzy minus rxy, and then plus qxc pyz. And of course we know that the value here and here is equal value. This is also equal value. This is also equal value, which means we can cancel them all. Okay, and it becomes 0. Okay. Okay, and then that's it. That's it. The curl and divergence. We can also write something like this. For so if we have the divergence value, the positive value means we are going to take from this one point goes outside. Okay, so we call the P is becoming a source. Okay? When the divergence is negative, we call the P is a sink, like when you have when you wash your hands, the water goes to the sink, right? Okay. And that's it for the curl and divergence. Okay, maybe before we continue to the next sections, which is the line integrals, is there any questions first? Any questions? Okay, I think uh, okay, I think we can move to the line integrals. Okay. Okay. We move to next section. This is the line integral. So line integrals. So what is line integrals? So first, let me just recall what we have in the normal integration. Okay. So recall that we have the definite integral from a to b of f of x dx. We can represent these terms as area under f of x, right? Or if we try to graph, if we try to graph, this is simply, if we have let's say the function is just like that, and we have the a and b over here. This integrations means that the integrations this area, the total area from a to b under this function of x. Okay. Now, what we want in line integrals is we want to generalize. Okay? We want to generalize. So let's say this is we call the integrations of a function defined over an interval. Okay, this is this is practically what does it mean with our normal integral, right? So we want to generalize this. So generalize and become integration of a function defined not on the interval but on the curve itself. Okay, so we are not going to take this from one interval to another interval, but we are going to define this along the curve. Okay, and that's why we are going to start our definition from the curve. From the curve. To give you an idea, let me just give you a picture of what kind of curve we might have. Okay, we have four conditions. Okay, we have four conditions. We have smooth curve, which is practically just a curve with some curvy line, right? We have piecewise smooth curve. Piecewise means that in every turns it has different functions, right? It has different functions, but we say it's a curve. We can take from one point and we can move our hands or our pencils along that curve, right? Okay. And we may also have the third case. We call it a closed curve because we are going to loop the curve from maybe point A and then going back to A. So it's like a circular. Or if we remember, we can reparameterize. So we can use parameterizations to represent the loop. Okay, to represent the loop. So we add another parameter to help us mapping the curve, right? But it's not simple. It's not simple because it goes making this seems like an 8 number, right? Like a number 8, okay, for the C. But for the E, it's simple, just a circular, and then it's close. It's going back to the B. Okay. So we are going to take some terminology. Okay. Let's say curve C. Suppose, okay. So suppose the curve C is basically parameterized by f of t and g of t for x and y. So let's say, or maybe let me just write here. So R is a vector positions, so we can reparameterize with let me just write with G. Okay, your book's using F, but it's supposed to be the same thing. Let me just write G of t I plus H of t and J. And we can also write this in terms of function of two variables, f, x, y, okay, which is f, g of t, and h of t. I will directly go through here, and t is basically saying that it's coming from the interval of a to b. Okay. Okay, let me add an idea for why it's called simple. Simple is simply doesn't cross itself. While in C, you see that it has this, okay, that problem. It's crossing the curve itself. Okay, you will see later why it's becoming a problem. Now, recall, we have definitions. If we have the integral f of x dx, the definitions is, this is limit. Now, if we have um, the subpartitions, in your books, it's using the p like that. But let me just write first. Okay. So p is the subinterval actually. So we can write p is length of longest subinterval. We can also call this p as the norm of partition p. But basically, it's the same thing as we did in uh, in our calculus 1. Okay, now recall this, and then what we are going to do, instead of taking the subinterval on the interval itself, so for example, usually we take this, let's say this is the interval. Okay, let's say this is the interval. And let's say this is A is x0, this is B, this is xn, okay, and then we have some partitions here, right? Remember that we cut the rectangle in the integrations, right? And then we take this as maybe the sample value, the xk, and then we take and make this the subinterval making into 0. So making into really small. So making this so maybe we start with this rectangle, and then maybe we take it cutting in more small. So we are getting more, in approximately getting closer to what we are having in the real value of the area, right? But in the line integral, we are not going to cut the interval. So we cut the interval here, right? We make it into smaller rectangle. But what we are going to do in the line integral is we are going to cut the curve. So let me get you to the curve. So we are going to cut the curve like this. And we mentioned that the length of the small length here is the delta s of some k order. Okay. So we are going to have, okay, so the line integral means that we are going to have x, y, and then ds. So instead of dx as in a definite integral, we are going to integrate with respect to ds. ds is the arc length. Okay, this is the arc length. So we know the arc length, right? Remember the arc length definition. Okay. So this is basically, we cut this length, the curve. Okay, we cut this curve into some small arc length. Then we take that as limit. We say that as the p getting 0, or n getting infinity if you want to use n. N means the number of the cut, but p is the number of subinterval. It's the same thing. Your books using the norm p, the partitions. But you can also write, maybe if you prefer, write the n. Okay? N means the number of the cuts. Okay, it's practically the same thing. Okay. This is wrong. Not n. Should be. Oh yeah, it's n. So this is n. K equal 1, and then f. This is x k y k, and then the delta s. Okay. Where the delta sk is the arc length, right? So the arc length we can write with the arc length formula. Well, if you don't remember the arc length formula, you can approach the formula through the triangle. Okay, let me just give you later the triangle. So how we get this? Let me just quickly give you a review. Okay, let's take this as s. Take this as dx. Take this as dy. Of course, ds squared is dy squared plus dx squared. Simple, right? Okay, from there, the arc length. Okay. So that is the definitions. Okay. Now let me give you more general. So this is the general definition. General definition. Okay, let me give you the definitions. I will write with the same terminology with the books. Okay, so we will have the same terminology. Okay. Okay. Now, as a conclusions, we have the line integrals in plane. So we have first case is we can write the line integral, or maybe let me write the assumptions. Okay. Let g, so let g be a function. Okay. Be a function of two variables x and y defined on a region of the plane containing a smooth curve C. Okay, the first condition, the line integral of g along C, okay, from A to B with respect to x. Okay, that's the first case. We write the line integral gxy dx is equal limit as the partitions of p getting 0, some delta xk. Delta xk is the from this graph here. Okay, this interval here, and yk is here. Okay, and the second conditions is line integral of g along c from a to b with respect to y. So we are just going to change the dx to dy. So it's become okay. And in the third case, we can also write this line integral like we write before using the arc length. With respect to arc length. Okay, you can make it into these three conditions. Okay, and of course g need to be continuous. Okay, g need to be continuous functions on c. But then, of course, the question is, how can we practically calculate or compute our line integrals? Of course, this is just a definition. It's not really a method or using some techniques of integrals, right? This is just a definitions, right? So to calculate in practice, we need to parameterize. We need to have another parameters which is p, or any dummy variables that help us to evaluate. Okay, because if we are just looking at the x and y, we are not going anywhere because we have the two variables, and then we need to differentiate, or we need to integrate with respect to y or x or the arc length. Right? So the question is, what do? We need to solve this through parametric. So we are going to have another here, the method of evaluations. Okay. How to evaluate the line integral. So if we want to evaluate, for example, function of two variable x, y, let's say the x, what will happen? So what will happen is we need to evaluate from a to b, and this is going to have the dt. So or maybe let me set some assumption here. Some assumption. C is a smooth curve that parameterize by, let me write, x is f of t, y is g of t, and t is from A to B. Okay, let's say we have these assumptions. Well, at the beginning, I'm not really writing the same thing as here, but let me just write as similar with your textbook to let you know. Okay, so we have a function g define. Okay, now function g of f of t, g of t, okay, and then the dx is f prime t dt, okay? Because we can also look at from here that dx is f prime t dt, okay? Okay, and the other conditions, if we want to evaluate with respect to y, we're going to be able to check this with y. dy becomes g prime t dt. We can also look at here that dy is g prime t. And then last part, the evaluations we can also write using the arc length, the ds. The arc length, using the arc length, this is f prime t squared plus g prime t squared and then dt. So if you get, or if you are given the function with its parameter, with its parametric equation, and then you can definitely go through the evaluation method directly. Depends on which method you want to apply, whether it's dx, dy, or using the arc length. If the question is asking evaluate the line integral with respect to dx, then you're going to use this part, okay? If it is going to evaluate through with respect to y, then this is your method. If it's asking ds, then this is your result. Okay. Maybe we can move to how we can evaluate with some examples. Okay. 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 Did I have any parameter examples? I think no. Let me take the. Let me take. Okay. Let's just see this. Okay. Let's just see from your textbook this example. We have example 1 here. Okay. It's asking the this we have this curve. Okay, we have this curve. It's it's parameterized by this x equal 4 cosine t and y equal 4 sine t. Okay, and we are having t from 0 to pi over 2. Okay, so this is t0, this is t pi over 2 here. So first, we have three questions. We have integral, line integral xy squared dx, line integral xy squared dy, and xy squared ds. Now if we look one by one, okay, from the first one, we have xy squared dx. So we practically we just input the x and y from the parametric equations, and dx we get from the parametric one. We can differentiate the x and then we find the first derivative and we can plug in and substitute using substitution. And after some calculations, we get this sine cube t cosine t. We can use another substitutions to solve this integral, and we can have this as our solutions. Okay, I think it's not too difficult, and you can use calculators in your exam, so don't worry about some computations. Okay, and now the second method, xy squared dy. We just look at this is just plug in, and take dy, differentiate, and then we have sine squared, cosine squared, and we can take this into the uh, the trigonometric some identity. Okay, and then sine squared 2t it goes to using the cosine double angle formula, and then at the end simply you can just evaluate using calculators. I think you can just get this 16 pi, and then the last case we see that we just plug in and using the arc length, finding the arc length, and we find this, and using the substitutions again, once more substitutions, and you get 256 over 3. Okay, I think that's just for some examples that I think easy for just finding the solutions. Okay, maybe giving you another example. Okay, so let me give you another example from my questions here. So let the f of xy, we have a function here that is x squared plus y squared over 4 plus xy over 2. So compute line integral of f xy above circle of radius 2 centered at origin. This is the key. Okay. So you have some curve. Okay, you have some curve. You have some plane. Okay, plane. Some surface. Okay, you have some surface above the xy plane, and that surface is we are going to evaluate when we have the circle that has radius 2 centered at origin. So we don't really need to think like what kind of surface is that. We just know that we have this surface which has this fxy, and this is the equation. Well, what we do know is we need to have the circle which has the radius 2. So we have the circle here. So let me just giving you some illustration, or maybe let's say this is the circle of radius 2. So this is the plane that above the surface of the function fxy. Okay, Now, how do we deal with this? Okay, how do we deal with this? Now, because we don't really know what is the uh, parametric, right? What is the parametric of this uh, the functions? Okay, so let decide the vector positions. Okay, so first we need to parameterize, or maybe using the green color. Step one, parameterize t. So how do we parameterize t? We could see that we have circle of radius 2. So we can just use probably a circle x squared plus y squared equal 4. So consider that x squared plus y squared equal 4 is the circle that it has the radius 2, right? Consider that. Now to make this circle, okay, can we make with parametric? So can we parameterize this x to the variable t? So to make this happen, x should be equal to 2 cos t, right? And y should be 2 sine t, right? So this is our vector position. So we need to make this 2 cosine t and 2 sine t to make the radius becomes 4. Okay, because if we substitute going to be substituted here, it's true that it's 4, right? So let's make this as our parameterizations. Okay, and t will be going to be evaluated from 0 to 2 pi. Okay. Okay. Now the next part here, after we take the parameterize, step 2 is write the function in t in parametric equations. So since x is 2 cosine t, so since x is 2 cosine t and y is 2 sine t, so f this will be equal to, this is x squared plus y squared, so 4 sine squared t plus 4 cosine squared t divided by 4 and plus 4 sine t cosine t. This is xy. This is 2, so xy over 2, right? Okay. So we can simply write 4. This is 1, 4, and then 2 sine t cos t, or we can simply write sine 2t. That is our functions becomes. Okay. So this is what we call before g of t and h of t, right? And we have this sine 2t. So this is our functions that we need to take on. Wait, not sine 2t. 1 plus, sorry. Okay. Okay. Then if we have g of t is 2 cos t, ht is 2 sine t, then we can differentiate both of them. We differentiate, and we need this to take on the formulations of the line integral. So line integral becomes from 0 to 2 pi, 1 plus sine 2t, and then we take the, with using the arc length formula. Okay. So we have, this is 4 cosine squared t plus 4 sine squared t. So we have 4. This become 1, right? So square root of 4 is 2. So we have 2. So let me write 2 outside. 1 plus sine 2t. So 2 is multiplied with t plus or minus, because we integrate sine become negative cosine. This will be 0, so we have 4 pi. Okay, so let me just wait for a few moments so you can, if you want to take notes. Okay. Okay, let me just go back here, and I need just to mention, this is what we have if we want to take the line integrals in the integral with in the integration with respect to some parametric equation, some t. So we change all the variables into t, and then we can have this all this formulations. But we can also take, so if we define the curve like y equal f of x, so we can just define and take the line integrals with respect to dx. Okay, so for example, if you just take uh, so let y is a function of x, and a is our interval a to b. Okay, so we can use x as our parameter. Okay, so we can try this with dy is f prime x dx. Okay, and ds, we can take this. The first thing is this is from f prime. Maybe we can write this 1 plus f prime x squared. Okay. Or if you want to write in more clear, we can write from the beginning. So divided by the x squared, the x squared. So we have dy dx, then squared, and then plus 1. So that's why we have 1 plus f prime x and squared. Okay. And then the from here we can write that first the line integral gxy dx is just integration from a to b of just normal integral. Nothing really that really different from here, because y is just f of x, just taking this x and then f of x for the y. Okay. And second, can also take the dy and make it and changing dy with f prime. Okay. And the third one, if you want to take the arc length, you can change gx f of x, and then this become square root of 1 plus f prime x squared dx. Okay. So we can also have all this three statement if we have explicit functions, okay, defined by explicit function. So curve, this is we call the curve is defined by explicit function. Okay. Now what's happened if we have three variables? Well, in arc length, I think it's easy to just introduce if you have three dimension, that if you want that the line integral should be having z, sorry. Okay, we can just let adding the one more variable. But let me just skip first and giving you an idea on if we cut the curve. Okay, we cut the curve. Let's say we can have if, for example, if we have the curve like this and we want to separate this, let's say this is curve C. We want to separate this, become C1 and C2. We also can do that, and we can also make into our line integration. Okay, so we could say that line integrals we could say the C1 plus C2 Okay, of course, C1 and C2 depends on how the interval in the parametric way, right? In the parameters. And sometimes we can, like for example, if you have we can have this like dx like that, and then we have q x y, and then dy, and then we can combine this together and write as pxy dx plus qxy dy. Okay, we can combine this together because we have the same curve. Okay, we have the same curve, so we can do that. Okay. Of course, if you are thinking on regular integrals, we cannot do that, right? We cannot do that. We cannot separate or combine with different variables, right? Okay. But here we can do this. Or simply we could just say the line integral of p dx plus k dy. Okay. And now we can have the closed curve. So closed curve is okay. Now the closed curve we write with this circle in the middle, and then c, and then p dx plus k dy. Which means that the curve is going back to the original point, or it's going to have loop. Okay. So I hope you get the idea. Okay. The one way to think is first it's you have the dx and you have the dy. Okay. So if you think that uh, it will be having c1 p dx plus c2 k dy. We can also think here that when we combine these two, it's become a closed curve. Okay, we can take it, and we can say that probably it has piecewise definitions for the graph also. Okay. Okay. Okay, let me continue. So let's say we are having the closed curve line integral of closed curve y squared dx minus x squared dy. And let me just draw, it's the same as on your textbook. let me draw, and so this will be the x squared, y equal x squared. This will be another line here. So it's going to be here, going to be here, going to be here. Okay, so it's start from the origin, going to the right, going upwards, and then along the x squared, it's going back to the origin. Okay? So we are going to evaluate this closed curve. Okay, now if we see from the picture, we can conclude that the curve is piecewise smooth, which means piecewise means that we can separate becomes, let's say, C1, C2, and C3. Okay, so we can take the C1, C2, and C3, and smooth means in every piecewise there is nothing weird, so it's just as usual functions. Okay, so first we could take the let's just take this closed curve C. We can write this as C1, C2. Just my illustration, just to let you know that we have this three curve, okay, to make up the total curve. Okay. And C1, C2, C3 is the one that we are going to look here. C1, C2, and C3. So on C1, we take the parameter using x as parameters. Okay. And y is 0 on this C1, right? Y is 0, so dy is 0. So let me write on C1, this will be y squared dx minus x squared dy. Same as our original equation. Now we can write this becomes 0 dx, and it also becomes 0 for dy. So it's just 0. Okay, from 0 to 2. Okay. So this is 2 0. This is 0 0. I forgot to mention this. And this is according to x squared. This becomes 2 and 4. Okay. Okay, this is the first one. On C2, using y as parameter, from x equal 2 to x equal 4. So we'll write C2 okay. Then the dx will be 0. So x is 0, so dx is 0. Okay. Oh, not equal to, sorry. Equal 0. 0 to 4, right? Okay. And then minus 4, and then dy. And then we have negative 4 dy. This is negative 4y. From 0 to 4, it's going to be negative 16. Okay, negative 16. Okay. And then last curve is the C3. C3 we let's just use x as parameter. Actually, you can also use y, but let me just use x as parameter. Okay, this is from y equal x squared, and we can get dy from this y. So y equal x squared, so dy is 2x dx. So this could be taken from, so now from 2, so this is from 2 to 0. So from this 2 going back to 0, right? Going back to the origin. So from 2 to 0. That's why it's going to be 2, 0. And substitute x with substitute y with x, so x squared. So x4 dx minus x squared, and then this is 2x dx. So this will be 1 over 5x5 minus, this is 1 over 2 x4, right? So it's going to be x cubed, 2x cubed. So x4, so divide by 4, right? Okay. And then from 2 to 0. And you can compute this, and it is 8 over 5. So the total (0 minus 16 plus 8 over 5) is goes to be negative 72 over 5. So what negative means? So we could take this as if we see how we deal with this curve, we start from origin, goes to the right, goes upwards, and it goes back. But we could start from we could start from here also, right? We could start from there also. So if we have, for example, if we have this, let's say maybe going a bit down, let's say that there, from A to B. Okay, let me make another copy. So if you have this another one, okay, the first one we take this directions. Okay, we say that this is curve C. Now if you take another direction, opposite direction, this becomes minus C. So this is we call a curve with opposite orientations. Okay. So if we have the line integral negative C for the curve, we can also write that this is a negative of the positive C. So maybe let me write here, line integral, maybe going to be to the right a little bit. Okay, line integral is independent of the parameterizations of curve C, provided C is given same orientation by all sets of parametric equation defining the curve. So we could write this, or we could say this is equal to 0. These orientations, this having C and negative C, we are going to look at more in the next thing. If we still have time, we will see on Green's theorem, on Green's theorem. Okay. Now, since we already learned the line integral, some of the aspect that using this line integral, the easiest way to look at is the work in physics. The work in physics. So we can apply some applications. The work is basically it's the line integral of f and dr, the distance, the working distance. So this is our work done by the force. But I will not going into more details. This is just to see what kind of application that we might have. And another application is we call the circulations. Okay, so a line integral of vector field f around simple and closed curve C. This is a circulation. So circulation is equal to line integral closed curve and f dr. Or we can take this into f dot t ds. Okay. Okay, that's just some applications, and that's it, the line integral. But maybe let me just remarks for the line integrals in 3D or space. Okay. Let me just give you the the conclusions, okay? Because how we find and how we prove is basically the same with the two dimension. It's similar. So let me write g x y z dz. We can write as a to b g x. We can translate first into parametric. And then this is h prime t dt. So let the x, okay, assume that x equal f of t, y equal g of t, and z equal h of t, and t is from a to b. And then another line integral that we can have, that I think I already mentioned before, but let me just write again here to make sure that we have a more clear way here. Okay, just that. Okay. Okay. Line integrals finish. Okay. Okay. The next sections on the vector calculus for our course is independence of the path. Okay. We call this independence of the path. Let me write here. Okay. So one of the property that is important in line integrals is the path taken. So in line integrals, the path taken affects the value of integral. Okay. Okay, recall we have a vector field. Let's say we have the P and Q for each component at the x and y axis. Okay. and path defined by R, factor R, and let the T is from A to B. Okay. So we can also think this like F is like a force in the physics and path is like a distance. So we can think the line integrals is P dx plus Q dy equal line integral F dr. The dx and dy is it's from the R. R is f of t and g of t. So we could take the R and then differentiate the R, and we could take this as dx and dy. So the value is this value depends the value depends on the path C, okay, the path that's taken. So if we take, for example, let's just take some illustration. First, going from A to B from along this C1, okay. And then the second path, the same A goes to B for this C2. Okay. This integrations, the line integral C1 f dr is not equal with the other path. Okay, it's not equal. Now, I mentioned, I think in the previous page, that the vector fields can be called conservative, right? So let me discuss that conservative vector fields in more details. Okay, so conservative vector fields means that a vector function f in 2 or 3D space is called conservative if f can be written as gradient, which means the del, okay, the del of f, gradient of scalar function. Sometimes I'm writing small f, sometimes I write. In your textbook, it's written with this symbol sign. The function is called, this function is called the potential functions. So the function is called potential function. Potential function for okay. So basically, we can set up that f is the del of this sign, or sometimes I write using the small f. Sometimes. But I hope you remember. Before I write sometimes in psi, sometimes in f, small f. So this small f or this psi is potential functions. So if you can write, okay, if there exists, okay, the scalar function here, the scalar one, that when you deal with this, when you partial derivatives, there's exists this functions. If this exists, if this scalar function exists, it means that it's called conservative. F is conservative. So um, so we can say that F is conservative if exists a function psi so that F is del of psi. Okay, that's the definition of conservative. Okay. Okay. Um, okay, one more section. So this is small sections that related to conservative. Okay, one more sections. Or let me wait for you for writing this conservative factor field. Okay, so let me give you idea. So what is the implications? So if F is conservative, implications is this will be independence or path independence. So if value of line integral is the same for every path. So we choose path C1, C2, C3 all result in the same value for every path in region connecting to initial point A and terminal B. Then integral is said to be independent of path. So in other words, if you have line integral f dr of f along C is independent if for any two paths C1 and C2 between A and B. Note that if f is conservative, it will be path independent. Okay? It will be independent of path. Okay? And then it will raise a fundamental theorem for the line integral recall calculus. We have this is a fundamental theorem of calculus, if you remember, right? This one, okay. And in the line integral, so suppose C is path. It's a path in open region R, xy plane, and defined by RT equal x of t I plus y of t j. And then t is from A to B. And then the f, the vector fields is pxy I plus q. Well, let me write a little bit to the left. Qxy j. This is a conservative vector field in region R. And psi is a potential function. Potential function of f, where this A is xa, ya, and B is xb, yb. This is fundamental theorem. We will continue later to discuss more on this fundamental theorem. But I would just want to stop until here, okay, for this independence of the path. And after we know some fundamental theorem and then some concept and the implications of the closed path of the if we have some cases, and then we also need to know how to test whether the f is conservative, the vector field is conservative or not. So after that, we might continue to the Green's theorem, and after that, the surface integrals. So I think that's the best way we can take for our course. So this independence of path, Green's theorem, and surface integrals. Probably we stop until there. Okay, probably, and then we can focus on preparation for final exam. Okay, so I will stop until here, and I have some feedbacks. I think this feedback is uh, probably about the, I think matrix. I prepare for matrix. Okay, so let me uh, stop my screen for a while and having another feedback. Okay. Okay, so please join the other feedbacks. Okay. This is about the matrix. So if you have the notes before about matrix from, I think from the morning sessions and maybe from the previous weeks about matrix, you can prepare that as well. Uh, yeah, please join, because this is the way that I can know whether you attend the lecture or not. Okay, and also if you actively involve and maybe getting a correct answer, I can give you more and more points for uh, the course. But eventually, the point is not that much, but I hope it can help you at least for if you want to get like a really good grades. I think it can help. Okay, let's start. Write your student ID. Write your student ID. So let's start. 3, 2, 1. Let's get it together. Okay, just true or false. Okay, just 30 seconds. Okay, 10, 9, 3, 2, 1. Okay. Yeah, it's true. Okay. So the transpose, the determinant is the same as the original one. Okay. Okay, remember your name is your student ID. Okay, so if you have the chance to change your name, please change to your student ID. Okay. Okay. Okay, next questions. You can change your name actually. Okay, next questions. Find the determinant. Okay, I give you 2 minutes. Okay, 3, 2, 1. Okay, good. Okay. Okay. Okay, get ready for the next questions. I think this will be the last one. So 3, 2, 1, let's enter. Okay, I hope you still remember some theorem in matrix. Some theorem. Given that the determinant, that's if you have a straight line, okay, not a bracket, so straight line means that it's determinant. So if the determinant of A1, B1, C1, A2, B2, C2, A3, B3, C3 is 5, what is the determinant of the matrix B? You can see the matrix B. I think I mentioned this in the morning class, so I hope you still remember. Okay, 3, 2, 1, okay. Yeah, negative 5. It's negative of the determinant that is mentioned before, because if we change the row or we change the column, means that it's negative of the determinant of the original matrix. Okay, okay, great. So you're the winner, so I can give you more points for your grading system. And lastly, not last two questions. Can you give me your feedback on midterm? Okay, what do you think about the questions, the time, maybe how much you can work for the midterm, and do you think you are confident for the results that you can get really good? Okay. Lastly, write your student ID as usual, and maybe if another feedbacks. Okay, if you have another feedbacks, uh, yeah, anything you can write. I think your midterm results as general thing quite good, but I'm still waiting. This one student haven't got the midterm yet because of um, he's unable to come because he's on still on the plane, I think. So maybe wait. If not tonight, maybe tomorrow I will give you the results. Okay. Okay. Thank you for your attentions. We will see you again on Wednesday. So we continue on vector calculus. And meanwhile, please be aware. I will post the another quiz about Laplace transformation. Okay. So probably this week I will give you 3 to 4 days to complete it. So please check the Moodle. Okay. So thank you all. So I will stop the